Okay, welcome back. Last time we were talking about conservation of energy. I left a problem about the elevator. I wanna add another one, so you get some to help you thinking about that thing. Let's just say there's a just say there's a car or something. Right, this car is moving.
Yeah.
Then there's a person in there pushing it. Right?
Okay.
The car is moving that way. Right? The question is this person doing any work?
No.
Right. This is obvious, right? Okay. You think about the other one too. The elevator one. Okay. Also, the conservation of energy, conservation of momentum is more general. The two things collide or interact or whatever. The momentum always conserve. But conservation of energy, there are, you need to watch for friction, for whatever, the way the energy disappears. There is a have you ever seen this?
Yeah, but I don't know what it stands for.
Okay, c is the speed of light, which is, in other words, a big number. M is a mass. E is energy. Actually, to make it easier to look, probably it's better to do it like this. You know where nuclear energy come from?
No.
If the atom go under change, right, and the result has more has less weight, less mass than the beginning, that change of mass be turned into energy. Yeah. The for instance, a hydrogen normally has just one proton.
Yeah.
But then there are hydrogen that has two protons and hydrogen that has three protons. I mean three neutrons. I think hydrogen, this is two, three, that goes into a helium. This is one neutron and two neutron, and one proton becomes two proton and two neutron, right? That as a, this comes that comes with a neutron at the end. This weight is less than this weight. This is how hydrogen bombs are made, because nobody has able to make this reaction under control. So this nuclear power plants are not made this way. They're made by the splitting a heavy. This is the really light nucleus that make it heavier, and really heavy ones you can like uranium, you can split this up. I forgot, split up to something, some really weird elements. That gives up energy too. So there are different forms of energy you need to pay attention to. But this is more or less of a side note. Okay, let's move on. Let's say you're riding in a car, and all of a sudden the car starts to make a turn. We're going to take a look at this. What makes the car to turn?
When you like turn the wheel, then the front wheels turn, and like the back wheels like push it to turn that way, I guess.
True. Let's just say oh, this is a bad circle. That's better. Okay. Let's say right, your car is here, moving this way, right, with velocity.
Yeah.
And now, just move down, then move this way, with the same velocity of the same magnitude, different direction, right? So, what makes the change?
Isn't it just, yeah.
You have a velocity going this way, right?
Yeah.
You want to change this velocity to this direction. To change the direction of the velocity, but not the velocity itself. How do you do that? That's okay. I'm trying to draw a better curve if I can. I mean circle. Today is not my day. Okay, let's draw a smaller circle, so smaller difference. This goes this way, this goes this way, right?
Yeah.
F equals to M V dot, right? The change of V, the change of F. I mean, F caused the V to change.
Yeah.
Right. So you have two V's. You want to know what's F, right? The change of V is F.
Okay.
So I'm gonna draw this one here. Draw this V here. Right. Then I'm gonna draw a auxiliary line, as we said. This change. Let's call this theta, right? This is theta, right?
Yeah.
These two triangles are similar. You gotta go out and look for triangles. For instance, when we have a wedge, right? And then the fourth triangle is similar to the wedge triangle. Yeah, I probably didn't point that out. We should really point out those things. Now, this side, okay, let's look at this velocity and this velocity, right? This is difference of velocity. Let's say this angle is very, very small. When this angle is very, very small, this arc, I mean, is the same length as the straight line, right?
Okay.
When this is very, very small, when it's infinitely small, there's no difference. Make sense? Are you listening, even? Try, okay? You need to try. If you don't try, if you stop trying to understand, you'll never understand this stuff. You try, and then you get frustrated, right? You feel dizzy or whatever. Next time, you feel better. Otherwise, every time you feel dizzy, and soon enough, you get convinced you're no good at math or physics. Most of the people get convinced they're no good. They just never gone through the exercise, Yeah, try, okay? Okay, let's look at this. The distance. Let's do some. dv dt. We want to understand is dv dt, right?
Yeah.
That's this we want to understand. This, right? We want to understand.
Yeah.
Right? So we know this is dv is this edge, right?
Yeah.
we know this is proportional to theta is S and R. We call this R, right? Radius.
Mm-hmm.
V. But we obviously we don't know this. We don't know V and T, and then we just introduce something. We know theta.
Yeah.
Right? We know theta, and if dv d theta, we can do this. V difference is this. Theta is this. We can do it here. This we know this length, and we know this length. This is S.
Yeah.
Because let's say in period dt, right? This thing moved from here to here, and cause this velocity change.
Yeah.
So v, let's say v. How do I do this? dv. This is dv divided by this v, right?
Yeah.
That's d theta. That's let's just do this. This is dv. This is v, right?
Yeah.
And this is sort of ds. This is how much the thing is moving. So we know dv divided by v, that's d theta. Yeah.
Yeah.
D theta is always is also d theta times r is this ds,
Yeah.
right? So this divided by r oh no. This is actually the okay, this divided by, sorry, dt, this equals to wait, let's see, v, this is the velocity, right?
Yeah.
So in dt velocity, this thing traveled ds,
Yeah.
right? This is ds, this is dt, that equals to v, right? Okay, following me?
Yeah.
Okay, now let's look at this. Let's see. We want to know dv dt, right?
Yeah.
So dv dt is we want to know. Now we know this, right? There's no dv here. We'll put the dv in. dv equals to v d theta. Huh? We'll put this in. Oh yeah, d theta v dt, right?
Yeah.
Now this d theta dt is v divided by r. I just divide this down.
Okay. Yeah.
Now I put this in. V squared divided by r.
Mm-hmm.
You watching this?
Yeah.
Okay, now. In other words, okay, this is dv dt, right? Then I multiply m. Oh, okay. I had to multiply m in the middle too. Okay, I multiply m. This is the force. M v squared r. This force obviously is in this direction. When this angle is infinitely small, this is vertical to v. In other words, the force will be vertical to v, which is obvious. When the force is vertical to v, the magnitude of v is not going to change.
Mm-hmm.
You follow what I'm saying? You have a velocity, right? You put a force in this way, or acceleration actually. Just think about acceleration. You want this piece to accelerate that way, right? Mm-hmm. So this thing gonna veer this way, right? As this veers this way, right? your force going to change direction with it. Just keep being perpendicular to it. So this thing going to draw a circle. And the magnitude of this force is this. This is how much force you want to put on. In other words, let's put it another way. You're driving a straight line, right? Then all of a sudden you make a turn, right?
Yeah.
What do you feel first?
Yeah.
How do you feel? Are you going out or going in?
You're going out.
Yeah, that's we normally just think that's inertia, right? Because you want to go straight and then you get pulled over, so your body kind of keep going straight. So you feel there's a force this way, right? Right.
Yeah.
You feel the force this way because you're trying to use whatever you use to bend your body that way. Let's say you sit in the car, right? Your body swing this way, but you're trying to hold your body back. So in other words, you provide this force. So your body will make this turn. And that force is, of course, the seat gives you that force.
Seatbelt.
Or seatbelt, yeah. Okay, now, this is R, right? This is R. Let's look at, okay, look at this one. This is R, right? If you move with a certain velocity around this,
Yeah.
yeah, how long does it take for you to do a whole circle?
2 pi.
Right. What is it? How much did you travel?
2 pi r.
Yeah. You're traveling with a velocity v, right? And how long does it take for you to travel 2 pi r?
2 pi r divided by v.
Yeah, 2 pi r divided by v. This is the time that takes for you to travel.
Mm-hmm.
And we hate periods. We like frequencies. That's the in 1 second, how many circles you're gonna travel. So we look the other way around, right?
Yeah.
You remember angular frequency omega we introduced?
Yeah.
It's 2 pi f, right? Actually equals to v divided by r, right?
Mm-hmm.
So you put this in here, that becomes m omega square r.
Mm-hmm.
This is when we're talking about the spring. This is this we're talking about. You understand?
Mm-hmm.
When this is a natural frequency of the spring. When the spring moves around, we introduce this concept, right? Angular frequency. This is the same thing. Yeah?
Yeah.
Okay. How much time? 18 minutes. Maybe you can do something a little bit more. You feel like taking a break?
Mm.
Let's see what we can do. Okay. Okay, let's do this. Now, you understand, let's say moon goes around, doesn't matter what, let's say moon goes around the earth.
Yeah.
Yeah? This is the earth. This is the moon. And there's a distance, which is r. Yeah?
Yeah.
Let's say this kind of bigger distance. Yeah? This is the moon. I mean, this is earth. This is the moon. Following? The gravity, the let's just look at actually. Let me see. Actually, let's look at another. Yeah, we can look at this. Doesn't matter. The the gravity of this is proportional to the mass.
Yeah.
Okay. In other words, if mass gets bigger, there's more gravity. There's more gravitational pull.
Yeah.
And also is inverse of the r squared.
Okay.
That's understandable, right? Because for instance, if you're looking at a light bulb, right? If there's a light bulb or something, right? It gives out light in all directions, right?
Yeah.
You have this paper here, right? It gets a certain amount of light. Let's say you move out twice the angle. This is 1/4 of the light. Let's say this is, in other words, if this has got half the light, what how to say? No. If this is light on this is unit is 1, this is 1/4 amount. It's because this area of this ball, right? This whole big ball, the area is proportional to r squared. You remember the formula for this? This is r. This is r.
Yeah.
What's this area of this ball? I don't remember.
Area of
It's something r. R squared. I mean.
wait, the area of a ball?
A ball, yeah, a ball.
4/3 pi r cubed.
No. It can't be cubed. Cube is a volume. We're talking about the surface area.
Oh. No.
Cheat sheet.
4 pi
4 pi
r
r
squared.
squared. Yeah, 4 pi r squared. Yeah.
Yeah.
And now this is 2r. Let's say this is 2r, right? So this ball's area is 4 pi 2r squared, right? 2r squared, right? So in other words, this is 4 pi 4r squared. Yeah. In other words, the r extended twice, right? The area expanded by 4 times.
Yeah.
Yeah. So this is the light, the strength of light, because the same amount of light got distributed among the same area, among this area and this area. So this is 1/4 of the light that's on this. Yeah. That's the inverse proportional to r squared. And gravity somehow goes along that kind of a situation. That's easy to understand, right?
Yeah.
I think that was an assumption, and people try to measure it, and of course, it is that way. And then there's a constant. We call it gravitational constant.
Okay.
Also, the moon is moving with a certain velocity. Okay, omega. Right.
Yeah.
The moon actually is going away, but it's so minute, so little. Well, we will deal with that later. Let's just assume the moon's stable.
Yeah.
Yeah, moon's not going away. Yeah. So there's a force. There's a force. This force, gravitational force, is making the moon to run the circles.
Yeah.
In other words, this force, M, this is the force. The gravitational force is pulling the moon. It's pulling the moon, so the moon goes a circle. Yeah?
Yeah.
The moon's mass, we can cancel out. R can go down. So equals to G. This is how how fast the moon goes.
Mhm.
Okay. Of course, the moon is going away a little bit. So in other words, this is this gravitational force is a little bit less than this.
Yeah.
So it is letting it go on a little bit. Of course, when the moon gets out, there'll be a lot of problems. We're not going to talk about it because the moon helps stabilize the Earth itself, its rotation. When moon gets out, really gets out, the rotation of the Earth is going to have a problem, and then there will be a lot of problems. But that's not going to happen anytime soon, so you don't have to worry about it. We'll all be dead, long dead by then, so don't worry about that. But these are the things we want to, so at least we want to understand. Okay, let's say this is another moon. Let's say we want to send out a satellite,
Okay.
right? And this satellite, we want to just stay there, not moving.
Okay.
And then we want the satellite to stay not moving onto a spot of the Earth, just above the Earth on a certain spot. Stay there. Yeah? You hear what I'm saying? Of course, the Earth spins, right?
Yeah.
You know the angular frequency of that, right? It's a day. Every day it moves a circle, right? Around the equator, right? So
Yeah.
you know this thing has to be on the equator.
Okay.
So you want this thing to run, you want this satellite to run around the equator with a angular frequency of 1 time a day. So this angular frequency is set. Okay? The mass of the Earth, you know what that is. It's set. So you see a situation here. When this is certain, this is certain, this is certain. In other words, if you want to put out a satellite, right?
Yeah.
And that satellite, you say that moves with the Earth. It doesn't move relative to Earth's motion. That R has to be the same place. Actually, in reality, in other words, there's one circle.
Yeah.
Okay, this circle has been lined up. There's a satellite lined up on it, so that people can have satellites not moving relative to Earth. Okay, what else can we get from this? Oh yeah, let's do another one. Let's do the Earth, right? This is the Earth, right?
Yeah.
The Earth spins, right, with angular velocity. This is once a day.
Yeah.
Yeah. The gravity here and the gravity here is different
Yeah.
because the people here is turning. The people here not turning.
Yeah.
The person here just spinning by himself. So there's no centrifugal force on him. This one has a force, and that force we know. This is the radius of Earth. Let's call it R, right? It's this person's force. There's a force coming in, which is this. Then there's force going out, right? This person feels the force going out. Just like when you take a turn, when the car takes a turn, you'll feel a force going out.
But like, no one feels that.
When the car take a turn, do you feel the force throwing you out in your car?
Yeah.
Yeah. So when you're sitting here, when the Earth spins, you feel force out, right? No, I don't mean. I mean just theoretically thinking.
Oh, okay.
That force being balanced, of course, being balanced out by the gravity. Okay. So the gravity is m, this is gravity, by the way. This is gravity, right? M times, I mean the acceleration, right? Gravity is an acceleration, right? You feel the acceleration down, right? mg. Okay, never mind. The mg you're feeling in here. The mg you're feeling in here is this, right?
Yeah.
The mg you're feeling here will be, mg you feel here is g, your mass, Earth mass. I'm using small r. Let's just use the big R, make it easier, right? But here, there's another thing. Let's call this mg1. Same thing. But this has to minus this m. This, right? Okay, now let's actually calculate this. Every second, if you convert this from 2 pi per 24 hours into second, it's basically 7.3 10 to the minus 5s. Okay.
Okay.
And g is r is not g is r is 6.4 10 to the 6 meters. Okay. So we get let's see what we're talking about here. So the or you can put these number in and calculate this. Calculate what G1 and G2. Okay, and you get the difference of G, difference of these two G's divided by the G is about this. Okay, so it's very, very slight, the difference of G.
Yeah.
Here and here. That's why you just said you don't feel it, right? You don't feel 0.35. You know, when you go to Alaska, you don't all of a sudden feel you're heavier. And actually, it's a little bit more than that. The real number is more like 0.5%.
Yeah.
And that is because this R and this R is not the same. Earth is a little bit like this shape. R here is less than R here.
Yeah.
Okay, not that by that much, but just a little bit. Okay. Of course, if you're looking for somewhere here, right? That force is still going this way, right? Because you're spinning this way, right?
Yeah.
That force still going. The force is going out.
Yeah.
And let's call this theta. Okay. Yeah, this force is what?
That force is like pi over 4. So the force is, I don't know. Square root of 2 divided by 2.
Oh no. That is the. Look at it. Okay, let's do another thing. Look at this motion. Okay, look at this motion. The motion is on this, basically like this, right? On this plane, right? They're rotating this way. Yeah.
Yeah.
At omega, right? So you know this m omega square r. Omega doesn't change, right? You're still one day. A circle. R changed.
Yeah.
And R is what? The new R is what? This R is
Data. What do you mean?
what's this R? No, this is the big R. You're running a bigger circle. This now here you're running a smaller circle, right? So what is this R?
A small R?
Yeah, what is it?
It's cosine.
Right,
Theta.
right. M, right? Omega R. No, this R here is big R cosine theta. Yeah. So as the theta goes to 2 pi, this become 0, so to speak. Makes sense, right?
Yeah.
Okay, now I think we can. Yeah, perfect time. Take a break. See you later.